Welcome to this puzzle guide. In this puzzle guide, we will be discussing the well ordering principle, which is a very fundamental principle in mathematics. This is also equivalent to something called the principle of mathematical induction, which we will get to at some point in the course of the next few lectures. But today we'll be just discussing the well ordering principle, and we'll understand this via examples. Okay, so start with the set of natural numbers. So the natural numbers are 1, 2, 3, and so on. We do not include 0 in the set of natural numbers. When we include 0, it's called the set of whole numbers. Okay. So the well ordering principle says that every non-empty subset of natural numbers has a smallest element. And this is completely obvious intuitively. And this is not the kind of thing that I can prove. It is too basic to be proved. So we just take this statement as true. And using this, we can deduce interesting things. A different way to look at the same thing is, and sometimes this formulation is useful, is the following. So let A be any non-empty set and take f as any function from a to n. N is again the set of natural numbers. Then the well ordering principle says that there is an element A in the set capital A such that its value, the f value at A is smallest amongst all possible f values. So that's what this is saying. And this is also immediately clear from this statement that I've written here, because what one can do is let s, maybe, yeah, okay, so let s equals image of f, which, let us recall, means just the set of all points that appear as images of elements in the domain of f. And since A is non-empty, S is non-empty, and therefore S is a non-empty subset of the set of natural numbers. So we can pick a smallest element in it. So let's say n naught be the smallest element in S, and let A in A be such that f of A equals n naught. Why does such an A exist? Because, well, n naught is a member of S, and S is precisely those points which can be achieved as images of elements in A. So, of course, there exists such a little A. Okay. So, yeah, so I'm not trying to say that this is unique or any such thing. There could be multiple such things, but we just pick one. And now it's clear that we should have f of A less than equal to f of A prime for all A prime in capital A. And that's simply because f of A is n naught, which is the smallest possible thing in S. And f of A prime is also in S. So we trivially have this. And there's nothing very deep going on here. But now let us use this principle to solve a slightly non-trivial problem. Fix a positive integer, and s be a subset of the first 2n integers, first 2n natural numbers, with the constraint that the size of s is at least n plus 1. Right? And then the problem asks to show that there exist distinct elements in S such that they are relatively prime. Meaning what? Meaning there is no prime factor common to them. So an example of relatively prime integers would be 3 and 7. There are no prime factors common here. 4 and 7 are also relatively prime. 4 and 9 are also relatively prime. However, 4 and 12 are not relatively prime because 3 is a common factor. 3 is a prime, which is a common factor. All right. So a natural number n, so let n be some natural number. We say n is good if the above, if whenever s is a subset of the first 2n natural numbers with size at least n plus 1, then there exist, basically for which the problem actually holds, there exist two things. So two distinct things such that x and y are relatively prime. So in this terminology, the problem is asking us to show that every natural number is good So that's what we want to show. Every natural number is good. And therefore, we can consider those natural numbers which are not good. N is not good. So B secretly stands for bad. So consider those natural numbers are not good. And what we want to show that B is empty. This is what we want to show, right? That there is no bad natural number. So this might seem like a very verbose restatement of the problem and highly unnecessary, but just bear with me. So assume on the contrary that B is not empty. We want to show that B is empty. So assume on the contrary it is not empty, and we want to produce a contradiction. So by the well-ordering principle, there is the smallest element in B. Let n naught be the smallest element in B. So just find the smallest bad natural number. Okay. But note that this has to be greater than 1. Why? Because we can verify the truth of this problem for n equals 1 by computation. For n equals 1, this set is just the set 1, 2. And a subset of this guy of size n plus 1, it has to be of size 2. So that has to be the entire thing. Where if you pick two distinct integers, then you only have one choice, 1 and 2. And they are, of course, relatively prime. So that's it. So for n, so what I'm saying is that n naught, if were it equal to 1, it would be a good natural number. But n naught is a bad natural number, so therefore it has to be greater than 1. Okay. And now here's the thing. So let, since n naught is bad, there is a subset S naught of the first 2 n naught natural numbers with size of S naught greater than equal to n naught plus 1, and no two distinct elements of S naught are relatively prime, and no two distinct elements of S naught are relatively prime. Okay. So far we haven't done anything really. This is just a template of how the well-ordering principle is used. At some point we have to use the integrities of the problem, and I think this is the point where we do it. So we have this the set of all first 2 n naught natural numbers, which we will think of as, and the other two things I want to sort of keep separate. Sorry, this is a -1. Right. So this is the set of first 2 n naught natural numbers, basically that set. And I have written it in this way deliberately. Now S is a subset of it. So case 1, S naught is a subset of it. So case 1, S naught intersection, or let me introduce a notation. So let maybe T naught equals S naught intersection this guy. And now case 1, the size of T naught is at least n naught. So what happens is, since n naught minus 1 is first of all a natural number because of this constraint, this is a natural number, it is greater than 0, is not bad, or rather is good. Let me just say it's good. Why is it good? Because it is smaller than n naught. N naught is the smallest bad natural number, so any natural number smaller than n naught has to be good. So n naught minus 1 is good. And now what we have here under this case is a subset T naught of the first twice of n naught minus 1 natural numbers of size n naught minus 1 plus 1. We must have, by the goodness of n naught minus 1, we can find two distinct integers in T naught such that x and y are relatively prime. So I hope we follow this point. This is the crucial point. This is how we apply the well-ordering principle. This is where we are actually using the hypotheses and the exact nature of the problem. We had some bad natural number, and since it is bad, we can find a subset of size at least that much, such that no two distinct elements in this particular subset are relatively prime. Okay, what we do is, we just restrict that subset to this portion of the original big segment. And if that, if we had chosen too many elements from just this part, then by the fact that this particular integer is a good integer, good natural number, we can find two distinct chosen natural numbers which are relatively prime. So that's something that should be clear to you before you proceed. Okay, so the case 2 is that this is less than n naught. Okay, so this there is no writing needed from this point on. The thing is, if you've chosen a total of at least n naught plus 1 integers from this, but no more than n naught minus 1 integers from here, or in other words, less than n naught integers from this part, you have to have chosen both of these. Because even if you drop one of them out, the maximum you can pick from this set of size 2 n naught is n naught. You cannot possibly pick at least n naught plus 1 natural numbers. So once again, if you pick too few from this part, you have to pick both of them. And that too few is controlled by this number. If you pick less than n naught from this part and a total of at least n naught plus 1 from this much, you have to pick both of them. But these are two consecutive integers. Then any two consecutive integers are relatively prime. So that's that. So this case was finished by the well-ordering principle, by the goodness of this guy. And this case is, well, you're using what exactly is going on in the problem. That if there are too few from this side, then both of them are picked. And if both of them are picked, they are clearly relatively prime. They are two consecutive integers. They have to be relatively prime. Okay. So that's I find that a very nice application. And I want to make a comment that once we get used to this kind of reasoning, all of this template-y thing nobody writes. What we write usually is that let n be the smallest natural number for which the theorem has not yet been proven, or for which the theorem does not hold by way of contradiction. So we do not write all this, and a natural number is good if it confirms to the problem, it's bad otherwise, you collect all the bad things, pick the smallest bad thing. We don't do that. Although perhaps I will keep doing it for maybe some time in this course of the next few lectures on the well-ordering principle. But once you get used to this theme of reasoning, one just says, okay, pick the smallest natural number for which the problem does not hold. The conclusion of the problem is false, which is by assuming contradiction that, by assuming that the problem is actually false. So that's how contradiction proceeds anyway. So yeah, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.